Thank you all for giving me the opportunity to deliver a talk on the basics that we use in the field of microbiology, in the field of paramedical staff for the hospitals. Microscopy. Before starting the presentation about microscopy, my first slide, it is about the how we utilize the resources or what we study. The more we learn, the more we see. If you have the desire to learn, to read, to do, only then you can see beyond the limits. And the other thing, how many resources you have. If you don't know how to use the resources, it is never be enough. I have chosen this topic, microscopy, as from 10th onwards, our students, they start learning about it. They start using microscope, but even in their UG, PG classes, they are not comfortable. They don't know how to use it, how to get maximum output of it. If I talk about the history, the first microscope that was used, useful microscope was used by Anton von Leeuwenhoek. And you will be surprised, this person was not a scientist, not a researcher, not from a science background. He was a cloth merchant. And he was just observing the fabric using his magnifying glass. But his vision, his lust, his curiosity led him to develop a microscope. This picture is of that microscope, traditional microscope that he used. And nowadays, we have sophisticated microscopes in our lab, but still fails to get the useful out of it. This microscope, it is of single lens as the magnifying glass that we use. At that time, he observed tea scrapings, rainwater, peppercorn infusions. At that time, technology was not this much advanced. People who were having some unusual observations, they write letter to Royal Society of London. And whatever he observed in 16th, 17th century, it is still valid and it is appreciated by a microbiologist even these days. So, whenever we talk about the microscopy and we say there are two types of microscopes, one is the light microscopy, another one is the electron microscopy. In all the institutes, labs, we have the light microscopes. No doubt there are the variants towards these microscopes, but if someone says we have the electron microscope, we have something else, no. Maximally, our laboratories, they have the light microscope, and in the light microscopy, we have different variants. Bright field microscopy, it is there, dark field, phase contrast, fluorescent, and these days we are using the compound microscopes, we are not using the simple microscopes. After Anton von Leeuwenhoek, there was a gap of 200 years. No further development take place in this field. Reason? Good quality lenses were not there. A compound microscope was developed, but with minimal resolution and poor magnification. So, of no use. In the 19th century, the microscopy, it started flourishing again. Now, the principle of microscopy, what we can observe under microscope. One of my colleagues usually say, can we observe elephant under microscope? कि ਅਸੀਂ हाथी देख सकते हैं? People said no. Reason is, sir, it is too big. It is not only too big, but the light will not pass through the elephant. This is the reason. To observe anything under microscope, light need to pass. And this light, when it passes, it all depends the medium through which it passes. Refraction and refractive index plays an important role. I think in your +1, +2 classes you have studied this phenomenon where the people talk about when the light enters in a medium, it either bends towards or away from the normal depending upon the density. So when a refractive index is a measure of how greatly a substance slows a velocity of light and the direction along with the magnitude of bending by the medium. Air, its refractive index it is 1, glass, its refractive index is 1.3. How the light rays focus by the lens when we adjust the knobs, coarse adjustment and fine adjustment knobs, we tend to focus the specimen. That lens helps to collect the rays of light, then refract it and we observe it. This is the microscope we use these days. In most of our labs, this microscope it is available, and we usually call this microscope as light microscope. But some of my colleagues, they might have seen the traditional microscope where the source of light it was sun. Sunlight was used. That is also a light microscope. That is also a light microscope, but our mindset, okay, this is the light microscope, that is the simple microscope. That is also light microscope, that is also a compound microscope. Compound microscope means where we use combination of lenses. 2 or more than 2 lenses are there. Now, what is the capacity of the microscope to magnify the image? Magnification, it is not only the thing that is required when we work with the microscope, it is the resolution. These days we all are using the mobile smartphones, and we usually ask the vendor, what is the resolution of my camera? That resolution means what is the capacity of your camera to separate two closely placed points or objects. That is the resolution. And the useful resolution is must when we work with the microscope. Resolution, it is the ability of a lens to separate between small objects that are close together. And the minimum distance, it is determined by an equation called absorption. Lambda, it is the wavelength of light, and I think we all are from the science background. And when we use light as a source, the visible range, it starts from 300 nanometer up to 600, 700 nanometer. That is fixed. You can't go beyond it. Lambda is fixed, 0.5 it is fixed, and it is a refractive index. Refractive index, it is depending upon the medium. Air it is 1, glass it is 1.34. then theta, it is the angle when we work on the microscope. This angle, half of the angle, it decides theta. And sine theta, sine 90, its value is 1 and it's the maximum value. You can't go beyond it. You can't go beyond it. So the lenses with larger angular and numerical aperture, its resolution is greater and its working distance would be smaller. I think all of you have worked with the microscopes. When you are working with the microscope, you place the specimen on the stage and focus at 10x, objective 10x. If you have closely observed that distance between the objective lens and the stage, it is in centimeters. Once you focus it, then you shift it to 40x, magnification power 40x of the objective lens, and you observe the working distance between the stage and the lens, it decreases. And when you go beyond it, say 100x, the working distance further shortens. And we put a drop of oil, that increases the refractive index, number of rays entering the tube, it increases manifold, and we get better picture, better resolution, better magnification by the microscope. So we have the different objectives: 4x, 10x, 40, 45x, then 100x, numerical aperture, and sine theta, 0.1, 0.25, 0.55, and 1.25 up to 1.4, because oil and glass have the same refractive index. Focal length 40 nanometers, 16, 4, and 1.8 to 2 millimeters. Just it is touching the stage when we use the oil immersion. Working distance, it further decreases. Resolving power up to 0.2 micrometer, means you can clearly observe at least bacteria. I am not talking about the eukaryotic organisms, say blood cells or the eukaryotic cells. I am talking about the prokaryotic, especially bacteria, the pathogens. You can clearly observe under the microscope. And these lenses, scanning, low power, high power, oil immersion, these are parfocal. Parfocal means, I don't know you people are aware of or not, when we shift the lens from 10x to 40x, student have the mind, now my lens will touch the stage. So what they do, they rotate the coarse adjustment knob so that your lens, it should not touch the stage. But your microscopes are designed in such a way, once you focused your microscope objective lens at 10x, if you rotate the lens to 40x, it will be in focus. Parfocal means you can change the lens, but the object, the specimen will remain in focus. It will not change the focus. The specimen, it is in focus. So just the fine adjustment knobs, it is sufficient to see the specimen. Usually we commit this type of mistake that I would like to convey. The variants, the first one, the bright field microscope that we usually use, I have talked about the principle, what to do, how to focus it. Then the dark field microscope. Usually the bright field microscope, it is used for the stained cell. When we talk about bacteria, it is unicellular organism, and the contrast, it is minimal. Contrast is minimal between the background and the cell, water and the cell, so it is tough to observe. So what do? We do the staining, and that staining increases the contrast and we observe the organism. But What if you want to observe unstained cell, live cells, so that the staining solution or staining dye is not changing the morphology of the cell? So we have the dark field microscopy, variant of bright field. We are using the source light. Live unstained cells or organisms are observed. Hollow cone of light is focused on the specimen. Unreflected and unrefracted rays do not enter the objective. Principle is same, reflection, refraction of light. Only light that has been refracted by the specimen form the image. Field surrounding the specimen appears dark, while the object itself is brightly illuminated, because the light that enters in the hollow tube, it is the light that passes through the specimen, not through the background. So background is dark, while your specimen it is brightly illuminated. In your bright field, just opposite was there. Phase contrast microscope, again a variant of light microscope. We changes the phase of light. We know light move in a zigzag manner, that is alternate crest and tufts are there. So we change the phase, and that change in the phase helps to get a clear picture, to get the information about the organelles within the cell better way. Condenser of the phase contrast microscope, there is an annular loop, stop an opaque disc with a transparent ring that helps in producing the hollow cone of light. We have the annular loop over there that stops the light to enter from the all illuminated area. Only the light area that allows the from where the light enters, and once the light enters, then we have a phase ring. Again the phase ring, in the phase ring we have the grooves. That grooves results in further change in the phase of the light that enters in the specimen, and the light that enters through the specimen, it is retarded by half of the wavelength as compared to the light that pass as such without passing through the specimen. And both of these lights rays, when superimposed, they form an image, clear image of an object. Structures are revealed beautifully using the phase contrast microscope. Then we have the fluorescent microscope. Again the source, it is light. Source, it is light only. Here we use high energy radiations, low wavelength. Some molecules have the property to absorb light. They become excited and later release energy, and that energy is released. Now the light, it is of longer wavelength, it is emitted, and that longer wavelength light can be perceived, can be seen by our eyes, and we use it in the fluorescent microscopes. Here we use a mercury vapor arc lamp that produces the light. We have the exciter filter that allow the entry of shorter wavelength radiations only, from 200 nanometer to 400 nanometer. Mirror is there that direct the light to the specimen. Now specimen, it is stained with the fluorescent dye, it absorb the light, now get excited. Now after excitation it will come back to the base, emitting the radiation of longer wavelength. Again we have a barrier filter over there to avoid the entry of UV radiations, lower wavelength radiations to our eyepiece, to our eyes, to protect our eyes, and we can see the objects by the fluorescent microscopy. Here we use the immunological assays using the fluorescent microscopy. Then comes the electron microscopy. These days, electron microscopy in our region, GNDU, Punjab University, even the Central University Bathinda, they own the electron microscope. We don't have. Our institutions don't have the electron microscope. Generally students say we have the electron microscope. We are not having. Here we use electron beam as the source of radiations, and those electrons can be directed, can be focused. They can illuminate the specimen, and the resolution, it is increased beyond the limits. If we compare the light and the electron microscopes, magnification in the light microscope, whatever the variant is maximum 1500x, 1500 times. But when we talk about the electron microscope, it may reach up to 5 lakhs, over 1 lakh. Resolution 0.2 micrometer, and in electron microscope it is 0.5 nanometers. You can observe viruses using the electron microscopes. Radiation source, visible light in our labs. Electron microscope, it is the electron beam. Medium of travel, we keep our microscope in light microscope in the tabletop, while electron microscopes, these are operated in vacuum. Type of lens, here it is glass, and in electron microscope we have the electromagnet. Source of contrast, differential light absorption when we use the dyes. Here the scattering of electron. Then the focusing mechanism, we adjust the lens position mechanically using the coarse and fine adjustment knob. And here we use current to the magnetic lens, we variate it. How you can change the magnification? We rotate the objective lens. Electron microscope, again we adjust the current. Specimen, we usually prepare the glass slide in light microscopy, and in electron microscopes we use the metal grids. Copper grids are there on which we mount our specimen. So range, what you can observe using the electron microscope: epithelial cell, red blood cell, bacteria, mycoplasma, viruses, proteins, amino acid, even atoms. It is possible. In electron microscopy we have two variants, SEM and TEM, scanning electron microscope and transmission electron microscope. As the name indicate, transmission, through which the electron transmits, passes. Scanning, where the electron is not passing, they are just scanning the surface. A heated tungsten filament, it is used for generation of electron beam. Electron can't pass through the glass. Electromagnets are there. We have the columns. Denser region in the specimen scatter more electrons and therefore appear darker in the image, since fewer electrons strike the area of the screen. The specimen, in the beginning I talked, when can we observe elephant under microscope? No, refraction. And whenever we prepare the specimen, tissue the section ਕੱਟਦੇ हैं ਅਸੀਂ, you use the microtome. ਮਾਈਕਰੋਟੋਮ ਯੂਜ਼ ਕਰਦੇ ਹਾਂ ਅਸੀਂ, ਪੈਰਾਫਿਨ ਵੈਕਸ ਹੁੰਦਾ ਹੈ ਅਤੇ ਉਹਦੇ ਵਿੱਚ ਸਪੈਸੀਮਨ ਨੂੰ ਮਾਊਂਟ ਕਰਦੇ ਹਾਂ, ਉਸ ਤੋਂ ਬਾਅਦ ਅਸੀਂ ਸੈਕਸ਼ਨਸ ਕੱਟ ਕਰਕੇ ਉਹਨਾਂ ਨੂੰ ਆਬਜ਼ਰਵ ਕਰਦੇ ਹਾਂ. ਬਟ ਵੈਨ ਵੀ ਯੂਜ਼ ਦ ਇਲੈਕਟ੍ਰੋਨ ਮਾਈਕਰੋਸਕੋਪ, here we use an instrument that is called ultra microtome. Ultra microtome that cut the bacterial cell. Just imagine bacterial cell ਦਾ ਸਾਈਜ਼ ਕੀ ਹੈ, ਤੇ ਅਸੀਂ ਉਹਦੇ ਵੀ ਸੈਕਸ਼ਨ ਕੱਟਦੇ ਹਾਂ. ਕਿੰਨਾ ਕੁ ਥਿਨ ਸੈਂਪਲ ਹੋਏਗਾ, ਸਪੈਸੀਮਨ ਹੋਏਗਾ, ਜਿਹਨੂੰ ਅਸੀਂ ਇਲੈਕਟ੍ਰੋਨ ਮਾਈਕਰੋਸਕੋਪ ਟਰਾਂਸਮਿਸ਼ਨ ਇਲੈਕਟ੍ਰੋਨ ਮਾਈਕਰੋਸਕੋਪ ਦੇ ਅੰਡਰ ऑब्जर्व कर रहे हैं. How it works, we usually take the picture on the fluorescent screen on the computer. How the specimen it is prepared for electron microscopy. 20 to 100 nanometer thick a typical bacterial cell, its size it is 5 micrometer, and we need a specimen less than it, 20 to 100 nanometer thick, 1/50 to 1/10 of the diameter of bacterium, and able to maintain its structure when bombarded with the electron under high vacuum. Electrons are easily absorbed and scattered by solid matter, so thin slices can be viewed. Specimens are fixed with glutaraldehyde, osmium tetroxide, dehydrated, then soaked in unpolymerized liquid epoxy plastic, then cut with the ultra microtome, and this specimen then it is observed under the microscope. Before observing, we go for the staining. Biological macromolecules contains hydrogen, carbon, nitrogen and oxygen only. These are the 4 elements present in the cell in the biological system. Almost same atomic number, nearly same atomic number, and electron scattering it is fairly constant. So what we do, we stain the cell with the heavy metals like lead citrate or uranyl acetate, bind to the cell structure, make them electron opaque, and increase the contrast, and that contrast helps us to observe the specimens under the microscope. This is the variation that we use. Metal shadowing it is there. Heavy metals such as platinum or gold, it is sprayed at the angle so that microbes, these are stained from one side. Metal piles up on the one side of the specimen, and uncoated area on the opposite side leaves a clear area behind its shadow to observe the 3D picture. Freeze etching, it is another variant that we use. I will not discuss it in detail. This is scanning electron microscope to observe the surface of the microorganism in great detail. Here the surface topography of the specimen it is observed. Electrons are emitted by an object surface rather than from transmitted. Electrons are not transmitted here. Specimen preparation is easy, no ultra microtome is required. You just prepare the powdered sample, and that powdered sample is filled in a cavity, and that is placed in the scanning electron microscope. 3-dimensional view can be observed. The electron gun, this is the system we use in the scanning electron microscope. Comparison between the electron which are not scattered and the electrons scattered by the specimen, that helps us to observe the specimen. This is all about the microscopy, basics of microscopy, how we do, what to do, what type of precautions we need to take care of. Thank you.